So now in this lecture, let's now relate your polar and rectangular form. So with help of some basic trigonometrical and as well as the complex uh, methods, we can able to arrive at some formulas. Okay, so in last class we have explained this particular rectangular form. So where we have defined the z as x plus jy. So we know in real the real axis will be lying on the x side and imaginary will be lying on your y axis. So this is your, let's say you have an x component, you have some magnitude of x component, and let's say you have some y component over here. So if you try to just relate a vector, it looks like a rectangular form. So that's the reason why we named it as the rectangular form, because your x and y is just representing the rectangular method. So whenever you draw this particular vector over here, so you can say, so this is your r and you have an angle theta over here. Okay, so your r is nothing but, so based on your Pythagoras theorem, you can say, so r, which is your hypotenuse, is nothing but square root of your both sides x square plus y square, right? So with this we can able to get my r, so which is basically, it will help me to get the magnitude of this particular vector. And the other thing is, like from here you can able to say that you have the function, we can define function tan theta, because you have components x and as well as y. So you can just say that the tan theta, which is nothing but, it is your the angle which is basically opposite, which is y. Okay, so your r is representing the magnitude, so this particular vector. Then your tan theta is going to represent the relation between your x and y, so relation between your magnitudes, so how it is getting related. So tan theta representation is nothing but x by y, your opposite side. Sorry, I have just written, sorry, so it is, so your opposite side is actually y, so it is y by x. Okay, so from here you can just say your theta is nothing but tan inverse of y by x. So with this, with the help of this, you could able to get both your magnitude and as well as the theta. So this is the representation of your polar form, because you know the polar form is represented as z equal to r theta, right? So similarly you can able to get other components. So if you want x and if you want y individually, then you can say, so your cos theta is nothing but, it is nothing but adjacent by x by r, hypotenuse is r. So hence you can say, you can define x as r cos theta, and similarly sin theta is nothing but, it is y by r. So where y is equal to r sin theta. So from here you can also get, if you substitute in your rectangular form, so you could able to get z equal to, so r is common, cos theta plus j sin theta. So this is how you are relating both your polar form and as well as your rectangular form. So I am repeating once again. So this is general representation of a rectangular form, and this is your representation of your polar form. So in order to get your r and theta, so you know that r is representing the magnitude, this particular vector, so which is basically the x and y components you need to get. So r is nothing but the square root of these two components, x square plus y square. And if I want to compute this theta, then what are the components which I know? I know what is your y, I know what is your x. So based on which I could able to derive my theta over here. So with that I can able to represent this form for your polar method. And similarly, in order to solve my rectangular form, I need my cos and cos theta and sin theta value. So based on which I could able to get my x and y, and finally I could able to relate with my rectangular form. So with the help of this you can able to relate. So your rectangular form and as well as your polar form. Okay. So the next thing is, so the idea of phases, generally it is related with your Euler's identity. So Euler has come up with one particular approach with help of your exponential form. Okay. So the exponential form, which is relating both your the cos theta plus j sin theta, is a representation of e power j theta. This is generally called as the exponential form. So exponential form relation is generally given by Euler's identity. So Euler has come up with this particular approach, that he is telling this particular function is finally helping me to conclude in one particular form, which is basically the rotation. So this is nothing but the representation of your rotation. So as you know, so whenever you are trying to compute its magnitude, so cos square plus sin square theta, which is actually leading to the value called 1, so which is nothing but representing that it is a unit circle. So this is nothing but the exponential form representation is in the Euler's identity, it is nothing but it is a rotation. So it is representing the unit circle. So unit circle is nothing but the rotation around the all your real and imaginary axis. So because I will relate this particular thing finally, because whenever we are seeing in graphical representation, it is easy for you to observe. So I will tell you the concept about this particular method later when I am relating with my actual sine and cosine functions. Okay. So so as of now, you just keep in mind. So your exponential form is nothing but it is going to follow your Euler's identity. So your Euler's identity is actually relating your rotation. So which is basically relating to your unit circle. Okay. So we know the physical model. So the time dependent model is nothing but v of t is Vm cos omega t plus theta. So where in v of t the Vm is nothing but it is in real. So basically you are trying to relate this particular time dependent function with your exponential form. So whenever you are relating it, your theta is nothing but omega t. So generally you can just replace this particular form from here to here. Okay. So this is the actual form which is after this. I hope you could able to relate this particular form. So I will just explain you even that. So here if you take, so Vm cos omega t plus theta. So where the cos theta, so this representation, which is basically can be related with e power j theta, where theta is nothing but omega t plus theta. So hence e power j theta can be represented as e power j theta with can be replaced with omega t plus theta. And your Vm is nothing but it is nothing but the magnitude. So whenever you are not representing any magnitude, it is assumed that it is 1, and similarly Vm over here, which is also equal to 1. So hence you can say the Vm is holding the magnitude of value 1. So basically relating to your unit circle. So this is nothing but holding the value of 1. So hence I can replace 1 by Vm, and I can replace cos theta by e power j omega t plus theta. Okay. Then I have just expanded this. So e power j omega t into e power j theta. So after simplifying this form, you can relate your v of t as Vm e power j theta. So why e power j theta? In your previous lecture I have explained that your complex form is completely time independent. Okay, and as well as it is relating my linear circuits. So hence your e power j omega t, the t is actually time dependent. Hence I am actually removing that form and I can able to relate as Vm e power j theta. So even I have transformed time dependent physical voltage into time independent form as Vm e power j theta. So I can just replace this as phasor form, which is relating e power j theta is